We're live. Welcome all.
All right.
Max Mountner. And this
Ben
is also
Jacobson.
Ben Jacobson. Ben, you're in SF. Sorry.
SF, Soma.
And I am in Berkeley, California. Also California.
Oh.
Like our previous 3 videos so far, we're working through MIT's Distributed Systems course. They have all of their lecture notes, problem sets, readings publicly available. If you guys want to follow along, there's a link which I'll drop in the chat real quick. There's also a GitHub repo that me and Ben are pushing our solved problem sets to, which I'll also send a link in the chat for. But just to catch people up, if you haven't watched any of our previous live streams, we finished the first lab of 4 labs, and now we're on the second one. But me and Ben are busy people, so we haven't read the lecture notes yet. So I'll screen share on my screen, and me and Ben will honestly probably read the notes aloud. Maybe we'll start reading the lab. I mean, obviously that's primarily what we want to do on these videos is code and solve the problem sets. So you guys should be able to see my screen now.
So we're done with lab 1, so we're going to be working on lab 2A, hopefully.
So this was previously taught this last spring. So this whole schedule has dates that are when the MIT course had readings due and problem sets due. We operate in Max and Ben land where we don't have due dates. But
jobs.
So finish lab 1, on to lab 2. Looks like it's got 3 separate parts that are due after 1 week. I'll open that in a new tab. But the readings and what this lab is primarily about is Raft. Raft is a replicated state machine protocol, which me and Ben can probably guess at what that means, but we should probably read the lecture notes.
Yeah.
Well, let's read a little bit of the lab because the lab's kind of long. Let's just read the introduction. This is the first in a series of labs, or do you want to go? You go, Ben.
All right. This is the first in a series of labs in which we build a fault-tolerant key-value storage system. In this lab, you'll implement Raft, a replicated state machine protocol. In the next lab, you'll build a key-value service on top of Raft. Then you will shard your service over multiple replicated state machines for higher performance. This example, key-value database achieves fault tolerance by storing copies of its data on multiple replica services. Replication allows the service, even if some of its servers experience failures, crashes, or a broken or flaky network. The challenge is that failures may cause the replicas to hold different copies of the data. Okay. Raft manages a service's state replicas, and in particular, it helps the service sort out what the correct state is after failures. Raft implements a replicated state machine. It organizes client requests into a sequence called the log and ensures that all replicas agrees on the contents of the log. Each replica executes the client requests in the log in the order that they appear in the log and applying these requests to the replica's local copy of the service's state. Since all the live replicas see the same log contents, they all execute the same requests in the same order, and thus continue to have identical service state. The service fails but later recovers. Raft takes care of bringing its log up to date. Operate as long as at least a majority of the servers are alive and can talk to each other. With such majority, Raft will make no progress, but it will pick up where it left off as soon as a majority can communicate again. In this lab, you'll implement Raft as a Go object type with associated methods meant to be used as a module in a larger service.
Okay.
Instances talk to each other with RPC to maintain the replicated logs. Your Raft interface will support an indefinite sequence of numbered commands also called log entries. The entries are numbered with index numbers. A given index will eventually be committed. At that point, your Raft should send a log entry to the larger service for it to be executed.
Okay.
Okay.
So like in the previous labs, there's probably some tests that are all failing, and that by implementing this Raft Go object, those tests will pass, and we'll have this Raft instance or instantiatable object that can do what they're talking about having it do.
Yep. I haven't heard of the Raft consensus algorithm, so.
Yeah, it's pretty recent. Like, I don't think this would have been taught in the course maybe 5 years ago. In fact, they have the extended Raft paper link here, and that's probably one of the readings for the course. Yeah, read Raft. It's from 2014.
Okay.
So, yeah, that's pretty recent.
Fairly recent. Yeah.
We should consult the paper and the lecture notes, I guess. So yeah, we'll be implementing most of the Raft design described in the extended paper, including saving persistent state and reading it after a node fails and then restarts. You'll not implement cluster membership changes, which is probably really hectic, where you add or remove nodes in the
node.
Yeah. Or log compaction / snapshotting, section 7. I know that Kafka is kind of known for having log compaction. So you can configure like your logs, if they get too large after a long enough amount of time, there's some way to compact into a smaller amount of disk space older log events, probably as you mark them as having been read or something like that.
Right.
So yeah, we may go read this draft paper, but it's probably gonna be heinous to read it. Might also not be. We'll see. Lecture notes. You may find it useful to look at this advice written for students in 2016 and this illustrated guide. Cool. For a wider perspective, have a look at Paxos, Chubby, Paxos Made Live, Spanner, Zookeeper, Harp, View Stamped Replication, and another paper.
Yeah.
Wow, that's a lot of reading. We're probably not going to do that. Probably you're going to start on the problem set. Hint, start early on this problem set. Although the amount of code to implement isn't large, getting it to work correctly will be very challenging. Both the algorithm and the code is tricky, and there are many corner cases. When one of the tests fails, it may take a bit of puzzling to understand what scenario your solution isn't correct and how to fix your solution. Read and understand the extended Raft paper, and the Raft lecture notes before you start. Your implementation should follow the paper's description closely. All right, cool. So 3 parts. We don't need a collaboration policy. F your collaboration policy.
We'll collaborate together on it.
Yeah. This lab does not involve a lot of code, but concurrency makes it potentially challenging to debug. Start each part early. Okay. So we already have the repo. I'll go open my terminal real quick. I'm in the GitHub repo that I sent in the group chat just now. You guys can see it right here. They're saying that the code for this lab is in source lab RPC. Nice, very simple. 2 files. This is a lot simpler than
2 files. Okay.
Previous lab.
All right. Okay.
They supply us with skeleton code in source Raft and a simple
Raft.
Yeah. So there's 2 directories: lab RPC and the Raft directory. So not too bad.
Still not that bad.
Let me see whether I have GoPath set. I do not have GoPath set. That's super annoying. I think I need to make it the lab. And now that I'm in, I'm going to Raft and run Go test. Cool, it works. Test initial election. Gonna fail.
Yep.
Election after network failure. Cool. So I guess we're going to be working out of the Raft folder or directory more than the lab RPC directory.
Yep.
The code. Implement Raft by adding code to Raft/Raft.go. Okay. Oh man, it's running all the tests. Let's not do that. These are really slow tests, by the way.
Yeah.
It took 30 seconds.
I wonder why they're slow, if there's like a bunch of setup that each one of these has to go through.
There's
I don't know.
probably like maybe not setup, but like similar to how Amazon Web Services or other services have listener or health checks,
Yeah,
which are based on time.
gotcha. So
It's like you gotta wait like 5 seconds.
5 second heartbeat or something, 10-second heartbeat maybe. I don't know.
Yeah, yeah. So I'll try opening raft.go and taking a look inside of it. What we're gonna do again? Implement Raft by adding code to that file. In that file, you'll find a bit of skeleton code, plus examples of how to send and receive RPCs or remote procedure calls. Your implementation must support the following interface. Okay. Which the tester and eventually your key value server will use.
Okay.
So there's a lot of comments, I guess, in the file, which is the case. It's a couple hundred lines of code.
Okay.
So got to be able to instantiate a new Raft server instance. Got to be able to start agreement on a new log entry, which I guess is I don't know. This I
Yeah.
don't know even how to read this kind of signature and go like, do you have any idea what's going on here? I am
Start
not sure.
raft agreement on a new log entry. rf.start.
We can look in here for the start method. Okay, the service using Raft wants to start agreement on the next command to be appended to Raft's log. If this server isn't the leader, the function returns false. Otherwise, start the agreement and return immediately. There's no guarantee that this command will ever be committed to the Raft log since the leader may fail or lose an election. The first return value is the index that the command will appear at if it's ever committed.
Hmm.
The second return value is the current term. Wow, that's a lot of return values. Anyways,
Okay. Okay.
I'm guessing that start is a kind of weird name for this method, and really what it means is log event. So it gets past um, command.
Oh, so it's start no. So, well, log event. It's start agreement on a new log entry.
So it's probably like we have one node of several nodes in our cluster
Yeah.
that are communicating with each other. And
Yeah.
command is a log entry that the given node that we're invoking start on
Yeah.
wants published to the other nodes, is my
Okay.
guess.
Yep.
I don't know if that's true or not, but
Yeah, I think that makes sense.
oh, wait, damn. The lab has everything. Uh, a service calls make to create a Raft peer. And the
Okay.
peer's argument is an array of established RPC connections, one to each Raft peer.
Okay.
The me argument is the index of this peer. That's
In the
called
peers
invoke,
array.
called make.
Okay.
In the peers array, start, given a command, asks Raft to start the processing to append the command to the replicated log. So the log is a series of commands, I guess.
Mm-hmm.
Start should return immediately without waiting for this process to complete. The service expects your implementation to send an apply message for each new committed log entry to the apply ch argument to make.
Okay.
Where was the apply ch? Looks like it's a channel.
Yeah.
I guess that's what ch might mean. We can look at what apply ch might be. Apply ch is a channel on which the tester or service expects Raft to send apply messages. So I'm guessing it's primarily for testing purposes to be able to see that we are acknowledging rights to the log or something like
Okay.
that.
Yeah.
Your Raft peers should exchange RPCs using the lab RPC Go package that we provided to you. It's
Okay.
modeled after Go's RPC library, but internally uses Go channels rather than sockets. So Go channels are inter-thread
Yep.
communication objects. So anything we're doing here, I'm guessing, does not translate easily to multi-computer setups. So we're just making a toy raft, I think.
Yeah,
Does that
but
sound right to you?
the API for the RPC should be very similar. So even though behind the scenes it uses Go channels, I'm thinking that it could effectively use other nodes and an actual RPC to do the communication, maybe.
Okay. Yeah, I believe it. I believe it.
Yeah,
Go channels are just very like they have their own syntax in Go that makes them a very unique data structure where you have even like syntax specific rules. Whereas if we have socket objects instead of channels, there's probably a bunch of code that we'd have to go through and change to make what we're working on here
yeah,
usable for with sockets and network stuff.
yeah, exactly.
Raft.go contains some example code that sends an RPC. Let's check that out. And it handles an incoming RPC request vote. The reason you must use LabRPC instead of Go's RPC package is that the tester tells LabRPC to delay RPCs, reorder them, and delete them to simulate challenging network conditions under which your code should work correctly. Don't modify LabRPC because we will test your code with the LabRPC as handed out. Okay, good to know. This lab may be your first exposure to writing challenging concurrent code, and your first implementation may not be clean enough that you can easily reason about its correctness. Fuck.
Okay.
Give yourself enough time to rewrite your implementation so that you can easily reason about its correctness. Subsequent labs will build on this lab, so it's important to do a good job on your implementation. Okay. Want to read 2A?
Sure. Implement leader election and heartbeats, append entry RPCs with no log entries. The goal for part A is for a single leader to be elected, for the leader to remain the leader if there are no failures, and for a new leader to take over if the old leader fails, or if packets to and from the old leader are lost. Run go test run 2A to test your 2A code.
So, yeah.
So this is the initial election of a leader. Okay. Maybe we should look at the test.
Yeah. So, looks like there's two tests: initial election and re-election. Looks
Okay.
like the test failure trace is for a non-test file. It's the config file. Probably because there's something we haven't done yet. So the two tests, well, I'll search this file for 2A. Like there's a couple mentions of it. I haven't configured Vim very well here. 2A. So here's the two tests. You got three servers. Make a config, whatever a config is. Is a leader elected? So let's look in config.go and look for check
one
leader.
leader. Yep.
Dang, this is pretty intense.
Yeah, this is complicated.
For our audience that hasn't been on any of our previous episodes of this, neither me or Ben actually write Go as a programming language in our full-time jobs. So one of the reasons me and Ben are doing this is to get an opportunity to learn the language. It just happens that this course taught at MIT decided to use Go, which I think is pretty unique among courses out there.
Yep.
So if you guys are experiencing headaches just staring at this code, trust me, you're not alone.
Yeah. Yeah. Although honestly, it's the best way to learn a language, I think, is just diving into a code base.
Totally agreed. Totally agreed. So yeah, looks like in Go that there's documentation strings that precede functions if you're lucky. Check that there's exactly one leader, try a few times in case re-elections are needed. So yeah, it looks like loops over 10 times. waiting half a second. So every time check one leader is invoked, there's 10 loops at half a second. So this adds 5 seconds to our test runs.
Yep.
And what it's doing is it creates an array, and it looks like it make loops n times, where n is the configured number of servers, I would guess.
Okay.
So in our case, 3, and checks if each of them are connected, quote unquote, to, I don't know what that means, but tries to get the state of that node and see whether it thinks it's a leader or not of other nodes.
Okay.
Last term with leader. So I think similar to how politics works is that there's terms over time.
Yeah.
And different nodes might be the president or what have you. So last term with leader is just a variable name that refers to the last term over time where there was a leader, because there's the potential for terms over time where none of the nodes were a leader.
Yeah.
If there's bad connectivity problems or
Yeah. Well, so there's two cases. There's last term with leader, with a valid leader, because could be, you have 0 leaders, or you could have greater than 1 leaders.
Got it. Yeah. And this is the fatal log statement. I don't know if this actually crashes your program. I don't think it does. When we ran the tests, which I'll do again over here, go test, I forget how to run, go test run just the 2A tests for this lab. Yeah, I forgot. I gotta export go path. So test 2A initial election. You can see. Oh, yep. It took 5 seconds.
Yep.
Expected 1 leader, got none.
Got none.
So here's where it says expected 1 leader, got none.
Yep.
Ideally, this check 1 leader function should return here.
Yeah, and so the thing that's responsible for this is the get state, which is part of the raft, I think, right?
Yeah. So this config object is getting passed around in the test, and that we're making right up here, make config.
What is make config?
This is something that's a little bit annoying about Go, is that it's really not easy to see where variables like make config are namespaced.
Yeah.
I'm pretty sure it's not in test.go, but rather in config.go, but you don't have to explicitly import it. It just needs to be in the same package, which makes it a little bit trickier if you use an IDE or text editor like I use, like Vim, as opposed to a more mature IDE that will, search across files, knowing how Go works and knows to read what package different files are. But needless to say, make config is in config.go.
Okay.
It returns this config object, and the config object looks like it's struct. Okay. So it's just some keys and values. And so rafts are an array of instances of raft.
Okay.
And raft is the file that we're writing.
Yep.
In order to make all these tests pass.
Okay.
So yeah, make config line 24 of the first test that we're trying to get passing. Is the leader elected? So since we have n is, I think, the number of servers. Yep. So it's the second argument when you're calling make config, and our second argument when calling make config is number of servers equals 3. Calling make config does a loop 3 times, and it creates 0.5 3 logs, or an array of like 3 that is the log files,
Okay.
which are just for each raft instance. There's
Yep.
an array. So
Okay.
it looks like it's a array of, well, it's a dict or hash map of ints pointing to ints. This is probably a very simplified version of a log, where we have like
Yeah.
our log row identifier pointing to the log value, which in our case looks like it's just integers. What does start one do? No idea.
Okay.
Down here, oh, it starts or restart a raft.
Okay.
If one already exists, kill it first. Allocate new outgoing port file names and a new state persister to isolate previous instances of the server.
So I think maybe we should add some logging to get state to understand what it's doing.
Okay. You want to do it in this for loop or inside of start one to see what start one's doing?
I was thinking inside the actual method get state. So check one leader is going to go through and look at all of the states of all of the rafts.
Yeah. So this is check one leader here.
Yeah. And so get state, there must be something inside each of these that one of them should think it's the leader, and we're not getting that. So
yeah, get state asks a raft instance for its current term and whether it thinks it's the leader.
Yeah.
So it returns probably an integer and a Boolean. So that's what term and is leader is. So we can look at the get state function, which we haven't really implemented.
Yep.
So yeah, your code here.
Yeah. So here. Okay. So your code here get state, and then maybe we can just log what that raft structure looks like.
Sure. So part of me is I go remember how to log. Totally. So I'll just copy this printf statement.
Yeah.
What should we print here? Make the font size a little bit smaller. Even though I'm on a very large monitor, it sucks because on the screen share it'll make things.
Yeah. Okay. I don't know. Let's just try to print maybe the object.
Okay. The RF.
RF
instance.
Yeah.
Okay. And then I'll try run the test again. Undefined. I gotta import funct. So yeah, we're just printing this raft instance. Cannot use RF as type string in argument.
Okay.
Yep, makes sense. So there's somewhere that we're going to be storing state of the raft. Looks like here's the raft struct.
Yep.
And it looks like we can or are expected to add attributes on the struct or keys on the struct. They're telling us to go look at the paper.
Yeah. Maybe we should go look at that figure. Yeah.
Oops. I made the font size super large because I'm on my big monitor. I don't want to screw people who are trying to watch on smaller monitors.
Yep.
The extended raft paper. So we can actually look at, so we're doing part 2A of the lab. We should be able to do part 2A without reading further ahead in the lectures beyond this one day of lectures and readings. So this is the paper that these guys wrote when they were like, oh, we came up with a new consensus algorithm. And figure 2, let's see what the hell figure 2 is. Whoa, oh, headache. Okay.
Oh, okay. So this is very straightforward.
Yeah. So
I'm kidding.
The raft struct that we're looking here, lines 42 to 52.
Yeah.
Looks like I'll bring this over here so we don't have stuff, and I'll make it a little bit bigger.
Okay. State.
So, state, that's the persistent state on all servers, current term. Well, let's add that over here. It's an int. I'll make it clear what's stuff that we were adding to the struct.
Is this figure 2?
The condensed summary of the graph consensus algorithm.
Okay, perfect. Cool.
The server behavior in the upper left box is described as a set of rules that trigger independently and repeatedly. Section numbers such as 5.2 indicate where particular features are discussed. Okay. There's a formal specification, which I think is a different paper. I think this is a citation to a different paper.
Okay.
What number was that? I don't remember. 31. So if we go to the end of the paper, 31 is another, Diego Angaro is the guy, one of the co-authors of this paper we're looking at right now. But it looks like that's his PhD thesis.
Okay.
So we could go look at that if we really want to, but we don't need to, because we're just trying to do the lab.
Yeah.
Okay.
Okay. So persistent state on all servers.
Latest term server has seen, okay, initialized to 0 on first boot, increases monotonically. Voted for is the candidate ID that received vote in current term, or null if none. So candidate IDs are ints, I think, since me, which is a reference to the raft instance's self, is the index into its peer. So yeah, we can probably add voted for int. And then log, which is the array of log entries. I think that's controlled, well, when we were looking at config, where we make config and these raft instances get created, this array of raft instances of length, number of servers.
Yep.
I think they initialize this array of logs. Whether we need to similarly define logs here or not, I'm not sure. But anyways, so yeah, it might have a log attribute. We can add that here for a moment. There's common syntax and go. Each entry contains command for state machine and term when entry was received by a leader. Okay, so
each entry contains command for state machine. Okay.
So it's an array of log entries, and a log entry is also a struct that's much simpler. It just has command, whatever that is, and a term, probably an int. So the log is just an array of these log entries, and these log entries are the term in which the log entry was written, and whatever command it was that's being logged.
Okay.
I'm just spitballing here.
Yeah, no. I think you're right. Yeah.
I don't know if we actually need to track log here since it's being tracked in make config, but oops, expected. Well, I think I added a Vim plugin for Go, and it added this actual checking, which is pretty helpful, but I had no idea. So there's some semicolon we need. 939. Oh, strapped. Cool. Volatile state on all servers. Index of highest log entry known to be committed. Commit index. Okay. And last applied. Index of highest log entry applied to state machine.
Okay. So I think we need those, and then I think we need the volatile state on leaders.
Which might be null if the raft instance is not the leader or whatever.
Yeah.
So commit index is an int probably. Last applied is also an int. And then next index and match index. So next index for each server, index of the next log entry to send to that server. Man, this is pretty involved.
Yeah. This is okay. We can figure this out though.
For sure. Let's go back to the lab real quick and see what all hints they talk about. Because right now we found this raft struct, which is what's being initialized in our tests, but we're not sure what the hell get state's supposed to do, or what we need to do here with get state. I mean, we could say term equals rf dot current term, right? Since we're now tracking current term.
Okay.
And then whether the server believes it is a leader or not. We should probably add an is leader key to the raft struct.
So if we go back to the
paper,
the figure, yeah.
Here we go.
Reinitialize after election for each server, index of the next log entry to send to that server. So maybe like leader can be inferred if like next index has a length greater than 0 or is not nil. That makes sense?
So I think next index is an array of length n, where n is the number of servers that our node knows of.
Yeah. But it would be nil. I don't think we even need these if it's not a leader.
So if next index is set at all, is what you're saying?
Yeah, exactly.
So just to get this on the screen, an example of what next index might look like in a cluster of, let's say our given raft instance is the leader and there are 2 others in the cluster, then it would be an array of length 2, and it would be the value, these integer values would be the value of the entry in the logs that needs to next be sent to the other 2 servers at this raft instances that this raft instance is the leader of.
Yeah.
So if there's no more to send, it might be nil. Like if the second raft instance in our cluster is all caught up, this might be nil.
Now, now I'm not sure.
Match index. For each server, index of highest log entry known to be replicated on server. So this is what our raft instance as leader expects to send next to its followers.
Okay.
Well, match index is what the leader raft instance knows that the followers have acknowledged writing or receiving. So while next index might be 2, nil, match index might be 1, 1. So these will probably never be nil. And it first initialized, these will probably all be 0 or something.
Yeah.
Our next index will be nil because we don't have any pending log entries that haven't been sent to followers. So back to what we were originally talking about, which was implementing the get state function for raft instances. You were saying that we may be able, instead of adding like a is leader bool, where we just say is leader equals rf.is leader, we may be able to, instead of that, we may be able to say like is rf is pseudocode for sure. If is rf.next index all nil.
Yeah, something like that. Yeah.
So then not a leader. So next index may be only non-nil if the struct is a leader, or that reference is the leader.
Yeah, I believe from what I'm reading, I believe that to be the case. Yeah.
Okay. Well, we can comment it out momentarily and say is leader equals true.
Yeah. Okay. Well, yeah. Let's try that and just see what we get in the test.
So it's going to say like in the test is going to say like all three raft instances think they're leader.
Right. Yeah.
Fail. Oh, god damn. Defined as leader. Oops. Oh, lowercase. Term 0 has 3 greater than 1 liters. Cool. Term 0 has 3 greater than 1 liters. Okay, so
perfect.
We're causing the test to fail in a different way. Let's go back and check out the lab hints, because they'll probably give us some guidance about a little bit about what we don't need to worry about how we'll submit our lab for grading.
Yeah.
We just need to get the test passing. But maybe some of these hints will give us an idea of whether we're on the right track by modifying the raft struct.
Okay.
I'm surprised that is leader is not something that this figure tells us we need.
Yeah. I mean, we can make a method that just takes a raft object and just returns is leader.
Sorry, say that one more time.
So just like the raft, like line 71 function raft get state, we could make a function raft is leader that we can then call.
And just return a bool.
Yeah. And then we could reuse it potentially if we need other places, but yeah.
We can call.
Yeah. Yeah. Well, look, I guess let's just try to return true here and then see if our test fails.
Okay. Should fail in the exact same way. Yep.
Okay.
So yeah, we'll modify this to do like Ben was just saying.
Yeah.
Yeah. So append entries is an RPC call, which looks like it takes a list of an array of entries to append to all of the cluster's raft instances logs.
Yeah.
So it gets invoked by the leader. It's also used for heartbeat checking to see whether the leader's followers are actually listening, probably.
Okay.
So while any given raft instance doesn't appear to have an is leader bool tracking variable,
yeah,
append entries does have a leader ID. And the reason this RPC takes leader ID as an argument is so that a given follower can redirect clients. Not sure what clients means here. Do you have any idea?
So follower can redirect clients. I'm guessing other clients of the other nodes in the consensus, maybe?
So a follower's follower?
Add append entries RPC leader arguments leader ID. Okay, got it. Redirect clients. So I want to append a log. I don't really know who the leader is, right? All I know is I have a cluster of nodes. So I send the message to one of the nodes. The node goes, "Am I the leader? Yes. I'll process this message. Otherwise, I'll forward this to the leader.
Got it. So if a follower receives a write,
Yeah, exactly.
instead of if a client is trying to communicate, yeah, got it.
I think that's got to be what it's doing.
There's no other notes about that value leader ID. In our lab, I don't think it's called append entries. We have, I think it was like not request vote, start. Yeah, we have this start method, which kind of looks like append entries. So we do have a request vote up here, and that corresponds to this RPC in the figure 2 of the paper.
Yeah.
But append entries, there's no such thing in this file. Oops, I don't think I have tag lists set up, so we can't look at all the methods in here. Yeah, there's no append entries method, so I'm guessing start is our append entries. So the service using Raft wants a start agreement on the next command to be appended to Raft's log. So rather than being able to just say write log entry, Raft requires starting agreement about writing the next log entry.
Okay.
If this server isn't the leader, returns false. Otherwise, start the agreement and return immediately. There's no guarantee that this command will ever be committed to the Raft log, since the leader may fail or lose an election. So basically, if not is leader, well, we can change this to rf dot is leader, right? If not is leader, I don't even know. Do you know the Go syntax for checking Boolean is not?
No, but we could try that.
Return false, right?
Yeah.
Well, it needs to be int bool. What are index term? Oh, we can just return index term. Otherwise, this is part B of the lab, so we actually don't even need to fiddle with this at the moment.
Yeah. I think so what we need to do is we need to update the make function.
Yeah. It is?
Yeah, so this is when it gets first initialized.
Okay. So I'll bring us back to the changes we made to the struct up here, lines 47.
Yep.
Yeah, you were mentioning we probably need to set current leader or current term equal to 0.
Yep, exactly.
Voted for, you should explicitly set it to nil.
Voted for. So voted for is the candidate ID that receives vote in current term. Okay, yeah, no, I guess.
Log entries, we should probably set that. I don't know if this is the right syntax. You know, I'm like so unfamiliar with Go. I think that's how you instantiate.
I think that looks right, yeah.
So there's arrays and there's slices. And arrays are fixed length lists, while slices are these variable dynamic length lists where they take care of resizing how much memory is allocated for the list.
Okay.
Versus an array where you explicitly say, I'm an array of length n or whatever.
Right.
We can comment this out for now because I don't think we need this for this part of the lab at all. Let me turn off my phone real quick. Okay, so we were modifying make for our to instantiate Raft instances.
Yep.
The service or tester wants to create a Raft server. The ports of all the Raft servers, including this one, are in peers array. This server's port is peers me. Okay, me is the index of this raft instance. All the server's peers arrays have the same order. Okay, we can assume that. Persister is a place for the server to save its persistent state and also initially holds the most recent save state, if any. Apply ch is a channel on which the tester service expects Raft to send apply messages. Make must return quickly, so it should start go routines for any long running work. So we're not doing any long running work yet, or they may already be doing that for us.
Yeah, so somewhere in here, I think we have to figure out a way to elect one of the things here as the
leader.
As the leader. Maybe I'll look up like raft election. I mean, it could be as simple as like me equals 0, right?
Yeah.
Like that's the naive
default to everybody thinking they're leader.
No, so it's only
or the first in the array. Got it.
Yeah, the first in an array is the leader. That's not very fault tolerant.
Okay. Let's check out the hints for the lab real quick because we're covering ground we've actually discussed but didn't realize they discussed in the lab notes.
Okay.
So, for example, add any state you need to the raft struct, which we're doing.
Yep.
You also need to define a struct to hold information about each log entry, which we also actually did. Here on lines 39 to 42.
Okay.
Your code should follow figure 2 in the paper, which is what we were looking at before, right here.
Okay.
Go RBC sends only struct fields whose names start with capital letters.
Okay.
Substructures must also have capitalized field names, e.g. fields of log records in an array.
Okay.
Okay. So maybe we want to capitalize term so that when log entries are getting sent from the leader raft instances to follower ones, the followers can see what term the log entry is for.
Okay.
Yeah, forgetting the capitalized field names sent by RPC is the single most frequent source of bugs in these labs. Got it.
Okay.
Glad we read that. Fill in the request vote args and request vote reply structs. Modify make to create a background go routine that will kick off leader election periodically by sending out request vote RPCs when it hasn't heard from another peer for a while. We'll see what for a while means. This way, a peer will learn who is a leader if there is already a leader, or become a leader itself. Implement the request vote RPC handler so that servers will vote for one another. Okay, let's check out these request vote args and request vote reply structs. Okay, nothing here yet.
Oh, nothing here.
So we need to make probably a elect leader. Well, I think request maybe request vote is what we're supposed to call in a go routine from within make. rf.request vote.
There's a structure in the figure 2.
Oh yeah, there is called request vote. RPC. Candidates term. Last log index. Last log term.
Results. Okay, so we just got to make these structures and then we'll figure out what they do.
Okay. So I'm similar to how we were adding the keys and values to the raft instance struct. We'll be doing the same here. So term is an int. Candidate ID is an int. last log
And they have to
index.
start with capital letters.
Oh yeah, because these are getting passed by
Yep.
RPC to
Yep.
between between Raft instances. Good call, dude. And then the results are current term for candidate to update itself.
Yep.
And vote granted. Cool. So yeah, like Ben was just saying, as we just read in the lab notes, Go RPC sends only struct fields whose names start with capital letters. Substructures must also have capitalized field names. For example, fields of log records in an array. Forgetting to capitalize field names sent by RPC is the single most frequent source of bugs in these labs. So while I was copying and pasting these struct keys, these state values, they're all lowercase, but we definitely need them to be all uppercase because request vote args is probably the struct that's used for passing as an argument to the request vote RPC down here.
Yep. Okay, so now receiver implements reply false
if term less than current term. So we can check, since we've added to our Raft struct this current term, which tracks a Raft instance's current term.
Yep.
That it has. You can say if rf dot current term. Sorry. If args dot term less than rf dot current term, you reply false. So I think that means we need to make a reply.
Okay. Yeah.
Well, actually, we're given a reply. That's what the RPC receives a reply handler.
Okay.
So reply dot.
I think it's just the same. Reply dot term equals args dot term. I'm guessing.
And reply dot vote granted. Yes. It was false. Yeah.
Okay, so wait. Vote granted.
If the term requesting a vote is less than the Raft instance's current term, then we vote no, whatever that means.
All right, and if voted for is null or candidate ID,
and candidate's log is at least as up to date as receiver's log.
Okay.
Vote.
Maybe let's just copy that string as a comment, and then we can implement that as well.
Sure.
I don't know.
So voted for. What is voted for?
Voted for.
Oh, it's one of the keys we added to the Raft instance struct, or Raft struct.
Okay.
It's the candidate ID that received vote in current term. Okay. If rf dot voted for equal nil, or
sure. Equals args dot candidate ID.
And this is a pretty involved bool. And candidate's log is at least as up to date as receiver's log. Grant vote.
Candidate's log.
So the candidate's log is this last log index.
Oh, I see.
So that's an integer referring to the candidate's sense of or record of the last log entry it's received.
Okay, and so we have a last
So if the candidate's last log index
is
is greater than or equal to, rf dot
commit index, I think, or index of the last applied,
maybe log length, the length of the Raft instances logs.
Yeah, but we have these other indexes. Yeah, maybe.
This was the array of other Raft instances and the index of whether they should be sent the next log entry, or the index of the next log entry they should be sent. So I think given Raft instances, the way to get where they are at in the logs is to check the length of their log.
Okay. Yeah, let's do
it. So rf dot log dot length or something like that. This is all pseudocode. That will probably break. So if voted for is null or candidate ID, and candidate's log is at least as up to date as receiver's log, grant vote. So I think that's the only difference.
Yeah.
Seems like setting reply.term equals args.term is redundant in both these cases. But if neither of these are true, like if the term of the vote is less than our given Raft instance's current term. So yeah, currently we're in the process of figuring out how to define request vote, the request vote RPC handler. So this is RPC handler. This is not the RPC itself. So,
okay.
Send request vote, I guess, is the RPC.
Okay.
This is a small wrapper around RPC sending.
Yep.
So Raft instances have this array of peers, which is the length number of other nodes, or all nodes.
Okay.
I think peers is an array of RPC or of sockets, of sockets. So it's an array of each socket of other nodes, or of nodes in the cluster. And a call is calling this RPC request vote.
Yep.
So does send request vote get called anywhere? It does not.
It doesn't. But I think we need to send a request vote when we make.
Yeah.
So let's go back to the hints.
So we've read up to, this is what we were doing just now.
Yeah. So we have args, we have reply.
Modify make to create a background Go routine that will kick off leader election periodically by sending out request vote RPCs when it hasn't heard from another peer for a while. This way, a peer will learn who is the leader if there's already a leader, or become the leader itself. Implement the request vote RPC handler so that servers will vote for one another.
Okay.
Okay.
So I think, yeah.
So we're going to call send request vote down here somehow. By the way, have we looked at these two lines?
No.
I think any shelling out to or go process or go background Go routine stuff we want to do is after calling read persist.
Yeah.
Kickoff election. So we're going to call rf.send request vote. Although it's send request vote, we need to give it the int of whatever server that we want to kick off the vote for. So we're probably going to loop over all of the peers.
Yep.
We're going to send request vote for I or whatever. Oops. Oh man, this stuff's passing out. Yeah. Line 153. Oh yeah, this is definitely not valid. So yeah, we're implementing a request vote, and we're also figuring out when calling make to create a Raft instance.
Okay.
How do we kick off the election? So yeah, doing the leader election periodically. We gotta the background, whatever background process we do is gonna need to keep track of like how long it's waited. So it's gonna be in a while loop or an infinite loop, keeping track of when was the last time we heard from up here.
Okay, so maybe we should just do an anonymous Go routine here, like go func, I think.
Wow, man, I gotta remember how the hell we do that. Closures, right?
Yeah.
So you can create an instance of a function, I guess is what they're talking about here.
Yeah.
All right, we can make a new function.
No, sorry. So what I meant was when
something even more go routine.
Yeah. So
go. Oh yeah. Define an anonymous function. Right
yeah.
Here.
So the next one. Yeah. Perfect. Yeah. So inside there, we can pass in peers. Yep. And then we need to pass in peers to that function at the very end. Yep. And then we'll, I don't know, sleep at the bottom of this function for 5 seconds, 10 seconds.
Whatever it is. Yeah.
Okay. And now, yeah, something like that, I think.
We're gonna want to add to our Raft struct like a last heard from peer timestamp or something like that. Last heard from any peer timestamp, and like rf last heard from any peer.
So that's going to be, so peers is going to be an array of lab RPC client ends. I wonder, yeah, okay.
I mean, I'm spitballing here about this last heard from any
peer.
Yeah,
I would say let's not do that right now, and let's just blindly send request votes to all peers every 10 seconds.
Okay. Oh, there's some weird, we gotta like do time times milliseconds to get at seconds.
Yeah.
So let's look at that time.sleep, I think is what it's called. Yeah. Oh, Raft election timeout.
Oh.
These are in our tests for this lab. Yeah, time.millisecond or something like that. Oops. We definitely need to import time.
Okay.
We can add log statements here. Since it's a GoFunc, I'm not sure whether printing will print the standard out or not.
I think it will.
Do you have any idea? Printf kicking off election.
Yep.
So we have not ran our tests in a while.
Yeah.
So now that we've added this.
Oh yeah, I guess we could. Yeah, let's. Yeah, let's run it, I guess.
So what we're expecting to see now when we run our two tests for the 2A part lab 2 part A stuff is we should see an infinite loop, I guess. Actually, we should. I'm guessing that we'll still see the same error.
Yeah, the test will fail, I think.
Yeah, with the same error, which is that we don't do any leader election yet, or we aren't properly electing a leader among our nodes.
Yeah.
So I think by default we're setting is leader or whatever to true. Oh yeah, get state. We're saying is leader. We have this function is leader, which returns true.
Yep.
So when our tests run, I think it's going to call get state even before we've had a chance to run an election.
Yep. Yeah. So it should do exactly what it's been doing.
So maybe we should default this to false for now.
Okay.
By default, our raft instances are not leaders.
Yeah.
So this should get us have our tests fail a little differently, or it should enter that infinite loop we just created. Well, because this is being ran in the background as a anonymous GoFunc.
I don't think we'll ever even see that. Well, I don't know. I don't know. I guess let's find out.
All right. Too many arguments to return. Line 153, first of all. I don't think we need to do that. I think it's implied that reply, we don't have any return value for this function.
Gotcha.
We're merely modifying a reply variable. And then lines 250 and 257. Or rather, we can comment that out for now. 257. It doesn't like our GoFunc. Here's is not a type. An array or something like that.
Oh yeah, the librpc client end array.
Where do you see that?
Line 240.
And that's to go. That's super annoying.
Yeah. And
okay.
Yeah. Okay. Cool.
We'll give it another try. Okay, kicking off election, kicking off election, kicking off election. Okay, so there's 3 kicking off elections printed right here. Probably one for each node. Expected 1 leader, got none. So 5 seconds elapsed and no leader was elected.
Okay, but we kicked off the election. That's good.
Mm-hmm. And then the second test failed similarly.
Okay.
Okay, so now we gotta actually do an election when we create our raft instances.
Yep. So
let's check out the test real quick. Make is not used in the tests. It's used in config. It's not even used in config, it doesn't look like.
Make?
Yeah. I'm trying to find where, oh, start one is our start or restart a raft instance. So this is where where new raft instances for our tests should be getting created. Here's a background process.
Yeah.
For monitoring whether we're actually calling RPCs or not. Ah, here's where we create raft instances. So our tests call the start one method. And this is how our tests create raft instances and create our cluster.
Okay.
So this is ultimately what our raft instances are getting, or what our make method, our make constructor is doing.
Okay, got it. So yeah, I think we should just try to get send request vote working.
Yeah, agreed. So we're gonna loop over all of our peers without checking the timestamp stuff.
Yep.
So definitely not doing that for loop, right?
Yeah. So
freaking A. How do we do that for loop again?
I don't know, but we need an index is really what we need.
This looks accurate.
Oh, for, yeah.
For in length of peers.
Okay.
Yeah. So send request vote takes a server identifier.
Yep.
Request vote args and request vote reply.
Yep.
So we need to instantiate a couple things. We need to instantiate a couple things for every send request vote RPC call we invoke.
Right.
So we need args and we need reply objects. So of our args, our reply, I think we can say we can do the shorthand assignment with Go.
Okay.
We can like do key value or something like that. You remember when us doing that in the last lab?
Yeah, I don't remember exactly how we create a struct like that. I think it's like curly brackets and then
Yeah.
The key and then equals the value, I think. And then new lines.
New lines? Oh, yeah. I think you're right.
Something like that.
We can actually go back and look at the previous lab to see that. Oh, it does not like that.
Doesn't like that?
Well, I think we got the syntax wrong somehow. Closer. Missing comma before new line in composite literal. 260. Maybe we need the comma. Yeah, cool. I mean, key and value are not right for show, but we can look at our map reduce lab. I think it was in our common map where we have our.
Oh, you know what we should probably do? We should probably on line 242. See how it creates a pointer to a raft and then it just sets them like that? Like, maybe that's what we should do for args. So we create args, the pointer request vote args, curly brackets, and then args dot key equals value.
I'm pretty sure they're identical. I'm pretty sure what's being done here. Yeah. I'm pretty sure this is identical. What's being done here as here.
Gotcha.
What we do need to do though is pass them in as arguments here. Args and reply.
Okay.
Need to do similar as you were saying, setting the keys of the struct. So the keys of the struct for request vote args are term, current term, Candidate ID. Oof. Dude, this is pretty involved. And we need same thing for request vote reply. We got a term in vote granted pool.
Okay. I think for the reply, we don't need to set any of those. We can just pass in an empty reply object.
Yeah, they can all be nil.
Yeah. And then
I think this is just me. And last log index and last log term to start can be zeros.
Okay. I don't know how Go functions work, but I'm guessing we're going to have to pass in RF.
To get me.
Yeah.
Yeah, I think you're right too, since it's a closure. So RF raft.
Yep. All right. Now all our tests pass. Not quite.
I think we just need to dereference our structs when we pass them in.
Okay, yeah.
It might be star or it might be ampersand. I'm not sure. Valid, indirect. Yeah, I think we need ampersand. Go, man. Oh, yeah, that was helpful. Cannot use RF as type raft in an argument to func literal. Maybe we need to do similar. Did what I just do there make sense?
Yeah. That makes sense.
We might not need the ampersand, but we do need the asterisks.
Yeah.
Yeah. Cool. So our tests are running.
Okay.
Still failing with the same dealio.
Okay.
But we are kicking off an election now, and we are sending a request vote.
Okay, I'm guessing it has to do with the last log index and last term.
Yeah, yeah. Or that our request vote RPC does not change any of our raft instances is leader value. Since we've hard coded our is leader function to return false.
Gotcha.
All of our raft instances are not leaders ever.
Oh, I see. Okay.
So we need to modify some state. Like that's something that was one thing that when we were reading this figure from the paper about keeping track of whether a given raft instance is leader or not, is that there's no is leader state, which I found really weird. Shall we read the lab the lab hints again?
Yeah.
We're making our way through them as it's kind of like chronological for the lab.
Yeah.
So fill in the request vote args and request vote reply structs. Modify make to create a background go routine, which we were doing. Kick off leader election periodically, which we're not doing yet. By sending out request vote RPCs when it hasn't heard from another peer for a while. This way, a peer will learn who's the leader, if there's already a leader, or become the leader itself.
Yeah, so we are doing that. We're doing it every 10 seconds.
Got it. So we are doing it periodically, but we're not
getting back anything valuable.
Yeah. This way, a peer will learn who's the leader, if there is already a leader, or become the leader itself. Implement the request vote RPC handler so that servers will vote for one another. Okay, so check out request vote again. That's where we started to do some stuff, but didn't get super far. So now we have a better sense of like how voting might work, or like they gave us this note about how voting would work in the paper about what the request vote RPC should do. but we didn't completely implement it. So one thing I'm curious about is, given that we implement this request vote handler with inside of this background Go routine, this Go routine will need to modify the we're going to need to get a peer's vote. We're going to need to capture the peer's vote. The send request vote actually has a return value.
Yeah.
It's this OK variable, which is just a true false. It's a bool.
Right.
But what do we do with this vote? And like, do we count up the votes?
Oh, no. So I think OK is just.
Oh yeah, it's not a vote. It's
not a vote. It's just the RPC was
worked or not.
Yeah.
Yeah. So we can throw that away for now. But basically, when an election is held, do we need to change is leader? So we don't have any tracking of whether a Raft instance is leader or not. That's what's so confusing right now, is that
yeah, maybe let's just make a Boolean leader and then we can figure out how to infer it afterwards.
Should that be on the Raft struct?
Yeah, on the Raft struct.
Should it be an int, like a pointer to?
I think it's just true or false, but
like is leader.
Yeah.
And it means whether the given Raft instance
is a leader or not.
A leader or not? You got it. We'll put it down here. So maybe we say just return is leader here. It's probably kind of confusing that we named this function is leader.
Yeah, unfortunately. Yeah. We can just comment that out, maybe. I don't know. Oh yeah, okay, perfect.
That's fine for now. But we're going to want to set here rf.isLeader equals false by default. Cool?
Yep.
But basically, depending on the results of the election, we need to determine whether our instance should declare itself leader or not.
Yep.
So no idea.
Okay, so
let's run this every 1 second. Let's run the election every 1 second. Does that make sense?
Yeah. Let me think for a second.
Okay. I gotta check. Nobody's trying to join the live chat. I don't know if that's limited to people in the Hangout or not.
I don't see anyone asking questions yet. Or
yeah.
We are at the top of Golang subreddit.
Brad.
Yeah. So that's cool.
Okay.
Okay, so let's look at the hints again. So
okay, so we're stuck on this hint right now. To implement heartbeats, define an append entries RPC struct. So that's from this here, append entries.
Yeah.
Though you may not need all the arguments yet. And have the leader send them out periodically. Write an append entries RPC handler method that resets the election timeout so that other servers don't step forward as leaders when one has already been elected. I don't know if that gives us any additional hint about how to track who's leader.
Yeah, I think we still need to figure that out.
Yeah, before that hint's helpful.
Yeah. So we have request vote args. We have request vote replies. So we need to do something with these results we're getting. Maybe we can just log the reply here. After send a request vote, we can log the reply to see what we're getting.
Okay, although I think send request vote is async. So like this will return immediately before the request vote handler for a given peer actually returns. So if we try adding, what I mean is if we try adding a print statement here, you know.
I think, I mean, it's an RPC call. I think it should be synchronous.
If it was, okay, we can give it a try.
But I don't know, or what does that structure look like? Because I don't know how to print the struct out. I don't know if that might just print like the.
We have term and vote granted.
Okay.
Can
we like turn that to JSON or something easily, or how can we see that in a log message?
I think we can just say vote granted. Yeah.
Okay.
And here we should probably add a statement if send request vote failed. That's how I think this is how you print with Golang.
Yeah, let's give it a shot.
And then apply to vote granted. That makes sense. So what's going on here? We're instantiating a new Raft instance. We're setting a bunch of default values. For example, current term starts at 0. We assume our Raft instance is not the leader to start. And since we don't know who's the leader yet, we kick off an election. Kicking off an election as a background Go routine.
Yep.
You know what we're not doing is this is actually not in a while loop. So this only runs once.
Oh, right. Okay, yeah.
So we need to make this a while loop. I think this is how you make an infinite loop in...
Yeah, I think so.
Oof, we got all kinds of problems when I added that. Golang infinite loop. It's probably super easy. Yeah, cool.
Oh,
that's
4.
Super easy.
Okay, 4.
I like that syntax. It's okay. Not that they care what I think. Okay, so cool. I'll add a new line there. The other thing that would be nice to see is probably what node is kicking off election. So we'll print kicking off election for yeah. We'll give it a try.
Okay.
Oof, it does not like string interpolation for some reason. Cool. So it's now kicking off the elections every 1 second, like we did down here, line 277.
Yep.
We're not actually doing anything with the results of the RPC that each of our.
So we got vote granted false for everything. Okay.
So the request vote RPC handler is what we're not doing. So if args.turn when we instantiate this request vote reply, we don't specify the return or any of the keys for that struct.
Yeah.
Do you think vote granted is defaulting to false, or that this block of code is being evaluated? Maybe we can add a print statement.
Yeah, let's
requesting here, requesting vote.
What is
term less than? Go ahead.
Sorry, why did we comment out the next block?
Oh, because it doesn't compile. It's like not valid. Go.
Oh,
this if block is like heinous. I didn't write it very well. All right, I don't even know the Boolean operator is like if or is right or if this is how you do
gotcha.
equality.
Okay.
So that's why I commented out. It's because our code wasn't compiling as I'd written it. Shall we try and work it out? Or I was going to add a print statement here.
Yeah. Totally.
Which one should I do first?
Let's add a print statement, I guess.
Print f. Peer requesting vote. Has term less than this draft instance's term. Does that make sense?
Yeah.
So we have a peer. They're trying to send an RPC to our Raft instance to request a vote. However, the term, their understanding of what term it is less than our Raft instance's term. So we definitely won't vote for them because they're behind.
Right.
So we're gonna tell them, you gotta catch up, motherfucker.
Yeah.
Let's see if that prints. Vote granted. So
it's not printing.
Yeah.
Okay.
This is an interesting blah. That one of the this is here. Definitely doing string interpolation wrong here. How do you delaying print boolean?
Yep.
Percent $t. Oh, I think we can use percent %v. V is like we'll infer.
Yeah. Okay. Yeah.
I'll do that here too. Let's see if that looks. Yeah, that looks a little bit more readable.
Okay. So we're not getting that log.
Yeah.
Although I'm not sure. Maybe we just don't see it, right? Like.
I think it's because all the Raft instances current term is 0 to start. So none of them have.
Let's add a log message not beyond the if, but actually just at the top of this function, just to see if we see it at all. Yeah.
Yep.
Okay.
So one thing we could add there is, since the request vote args has a candidate ID, which is the Raft instance that started the election, we can say args.candidate ID is requesting a vote.
Okay.
Of our Raft instance.
Okay, cool.
Oops. Oh. You want to grab it?
Wait just a second. I'll be right back.
Okay. So Ben's not here at the moment, but one of the things that we didn't do before we started the lab was read the lecture notes for this part of the lab. Um, and
All right, I'm back.
awesome. I was totally going on a ramble. I was going to start reading the lab notes because they're not very long,
Okay.
and I think they might clarify for
Okay.
ourselves and for our audience what part of what it is we're talking about.
What we're doing. Okay.
Um, I was also thinking about what time we want to finish today.
Yeah.
Are you down to go for, I don't know, much longer are you down to go for?
I don't know, maybe another hour?
Okay. Yeah, I'm down to go till noon.
Yeah.
Let me go back to screen share. Um, we'll check out the lecture notes real quick.
Yeah.
I'm going to take a mental snapshot of where we're leaving off, which was that we're implementing the request vote RPC handler,
Okay.
and that we were trying to see under what circumstances a raft instance would vote for another raft instance as leader.
Yep.
So I'll make the lecture notes full screen for a sec. They're not super long. Or maybe this will take us maybe like 3 or 4 minutes to read. You want to go?
Sure. So this lecture, raft elections and log handling. Overall topic, fault-tolerant services using state machine replication. Example, configuration servers like MapReduce, GFS master, key value storage server, put, get, lab 3. Goal, the same client visible behavior as a single non-replicated server, but available despite some number of failed servers. Strategy, each replica server executes same command in same order, so there remain replicas as they execute, so if one fails, others can continue. On failure, client switches to another server. Client being the person connecting externally to this group of nodes, I guess.
Mm-hmm.
A critical question, how to avoid split brain. Suppose client can contact replica A, but not replica B. Can client proceed with just replica A? If B has really crashed, client must proceed without B. Otherwise, the service can't tolerate faults. If B is up, but network prevents client from contacting it, maybe client should not proceed without it, since it might be alive and serving other clients, risking split brain. So I'm sending some commands to A, and someone else is sending commands to B. There's a risk that we then diverge, I guess.
Yeah, I mean it's like the bank. If you're a bank, you're managing
Oh yeah,
bank accounts.
here's an example. So split brain cannot be allowed, fault tolerant.
So client 1, I think C1 means client 1 and client 2.
Yeah.
So if client 1 and client 2 simultaneously try to set the value of key 1 to 2 different values, when client 1 goes to try and read the key that they just tried writing, chronologically, client 2 has overwritten the value, since that's what a non-replicated server would yield. But if 2 servers are independently serving the different clients due to a network partition or whatever partition, yeah.
Yep.
So the problem, computers cannot distinguish a crashed node versus when nodes are partitioned from each other. So we want a state machine replication scheme that remains available despite any one failure, handles partition without split brain. If too many failures, waits for repair, then resumes. So we're halfway there.
Okay.
You want to
go? Sure. So we want state machine replication scheme that's, sorry. So the big insight for coping with partitions, majority vote, 2F plus 1 servers to tolerate failures. Example, 3 servers can tolerate 1 failure. Must get majority, so 2 out of 3. F plus 1 can proceed. Why does majority help avoid split brain? At most, one partition can have a majority. So if you partition your servers in half, that can't be allowed. So there has to be some majority. The really useful thing about majorities is that any two must intersect servers, and the intersection will only vote one way or the other, and the intersection can convey information about previous decisions. Two partition-tolerant replication schemes were invented around 1990, Paxos and view-stamped replication. In the last 10 years, this technology has seen a lot of real-world use. The Raft paper is a good introduction to modern techniques. Okay.
So I think the Raft paper is straight up like a alternative to Paxos and view-stamped replication.
Yeah.
I think it probably references the two as like how it used to be done, but some of the real world use is probably having to do with distributed file systems like we were reading about with the previous lab, like Google File System and whatnot.
Yep. MapReduce, yeah.
Yeah. So Raft overview, state machine replication with Raft, lab 3 as an example. This is just plain text notes, so they're not slides. Right. So yeah, imagine clients, 3 replicas, a key value service layer, a Raft layer, and logs. Servers, Raft layers elect a leader among themselves. Clients send RPCs to the key value service layer of the leader node in our cluster. There's 3 types of RPCs: write, retrieve, add, or to I guess a key. Leaders, Raft layer sends each client command to all replicas. So it distributes writes to its followers, and each follower appends to its local log. An entry is committed if a majority have put it in their logs and acknowledged it to their master, meaning won't be forgotten. Like if one of the nodes crashes or for whatever reason or whatever. Majority will be seen by next leaders' vote requests. Servers execute entry once leader says it's committed. Key value layer applies put to DB. DB, is that database?
Yeah, I'm guessing, yeah.
Or fetches get result. Okay. Then leader replies to client with execution result. This is like acid, atomic consistent, idempotent. I forget what does the D stand for? I always forget. Acid, transactions, distributed, durability.
Yeah.
So does it get written to disk? Why the logs? The service keeps the state machine state. For example, key value database. Why isn't that enough? It's important to number the commands so they can be replayed, to help replicas agree on a single execution order chronologically, to help the leader ensure followers have identical logs and that they don't have different chronological orders of the entries. Replicas also use the log to store commands until the leader commits them, so the leader can resend if a follower misses some, and for persistence and replay after a reboot. So if some of the log commands are not performed to the given Raft instance or node of your distributed system, they can be replayed to catch that node up. Will the server's logs always be exact replicas of each other? I don't know, Ben.
I don't know. No, some replicas may lag. No, we'll see that they can temporarily have different entries. The good news, they'll eventually converge. The commit mechanism ensures servers only commit stable entries. Okay.
Okay, so eventual consistency, I think, is what they're getting at.
Yeah. So I think there's an agreement on a new log entry, and that goes back to the leader, and then the leader says, commit all your log entries
Up to a given
up,
entry index.
yeah, up to, yeah.
So the lab we've been working on so far, they're just giving us rehashing what the API is or interface is that we're implementing. So start. Oh man, this is really confusing lecture notes.
Yeah.
They're jumping to lab 3. So lab 3, I guess we actually implement a key value server like a Redis,
Yeah.
except
So,
it's multi-node.
so the put and get RPC handlers call start with some command, I'm guessing, like put value command or get value command.
Got it. It starts raft agreement on a new log entry. Yeah, this is what. Got it. Start returns immediately. RBC handler must then wait for commit. Might not succeed if server loses leadership before committing command. Is leader. False if this server isn't the raft leader. Client should try another. Current term, to help caller detect if leader is demoted. Index, these are all the return values from the start method. Log entry watch to see if the command was committed. Apply message with index and command. So this is a write to the log.
Yep.
So it's the name of the RPC call that raft instances send to each other, or that the raft leader should be sending to its followers when it receives a new write for the log. Raft sends a message on the apply channel. That's a Golang specific thing for each committed log entry. The service then knows to execute the command, and the leader uses the apply message to know when/what to reply to a waiting client RPC.
Okay.
There are 2 main parts to raft design: electing a new leader and ensuring identical logs despite failures. Okay. Cool. Now we're on the lab that we're working on. Okay. This is all we got left. Like maybe one more page.
Okay. So why a leader? Ensure all replicas execute the same commands in the same order. Raft numbers a sequence of leaders. New leader corresponds to a new term. Okay. Oh, okay. So term is like an election term, I'm guessing? Okay, a term has at most 1 leader or might have no leader. The numbering helps servers follow latest leader, not supersede leader. Okay. When does Raft start a leader election? Other servers don't hear from the current leader for an election timeout. So when does Raft start a leader election? Others don't hear from the current leader for an election timeout. So that must be the 10 seconds we put, or 1 second we have.
Yeah, if we go look at our make command, we have this background process when calling make to create a raft instance, which does the infinite for loop.
Yep.
And we have this commented out if check. So
I see. So timeout. Got it.
Yeah, we haven't. It's still commented out, but basically want to keep track of when was the last time this raft instance heard from any other peer raft instance, and if it's older than some value, no idea what that is, then we trigger an election. So when does raft start a leader election?
Yeah, so they increment local current term, become candidates, and then start election. Note this can lead to unneeded election. That's slow but safe. Old leader may still be alive and think it's the leader. Okay. How to ensure at most 1 leader in a term. A leader must get yes votes from a majority of servers. Each server can cast only 1 vote per term. Votes for server that asks. Okay. At most, 1 server can get majority of votes for a given term. At most, 1 leader. Okay. Okay. Okay, so how does a server know that election succeeded? Winner gets yes votes from majority. Others see append entries heartbeats from winner. The new leader's heartbeats suppress any new election. Okay.
Yeah.
Okay. Got it. Got it. Got it.
So I think from earlier when we were reading, maybe it was the paper or about, oh, holy crap, there's a rules for server section to that figure 2 from the paper that we hadn't looked at yet.
Okay.
Let's not look at it just yet, but
Okay.
basically there's this append entries RPC that Raft instances can send to each other, or node instances can send to each other.
Yep.
And usually it's an array of commands to be applied or to be written to each other's logs.
Okay.
But I think it can be that same RPC can be used as a heartbeat RPC if we
Gotcha.
just pass an empty array.
Gotcha. Okay.
So it can see, we can like see are the other nodes awake or whatever, or reachable.
Yep.
The new leader's heartbeats suppress any new election. Makes sense. So when we do an election and somebody wins the election, we can send, even if there's no new entries to be distributed from the leader to the followers, we can invoke append entries with an array of, an empty array,
Right.
and we can notify all of our new followers that the leader is writing or is invoking append entries.
Okay.
That probably also prevents having to hold another election super soon because everyone else is keeping track of when they last heard from a peer.
Right.
The new leader's heartbeats suppress any new election. Got it. An election may not succeed for 2 reasons. Less than a majority of servers are reachable. That would suck a lot. Simultaneous candidates split the vote. None gets majority. That happens when you have an even number of candidates.
Yeah.
Or nodes. What happens if an election doesn't succeed? Another timeout, meaning no heartbeat.
Yep.
And another election. Higher term takes precedence. Candidates for older terms quit.
Gotcha. Okay.
Okay. How does Raft avoid split votes? Each server picks a random election timeout. Freaking plain text lecture notes. Imagine
a diagram.
At which server's time. That makes sense. Intuitive. I think that makes some sense intuitively.
Yep.
Randomness. Go ahead. Go for it, man.
Breaks symmetry. One will choose lowest random delay, hopefully enough time to elect before next timeout expires. Others will see new leaders append entry heartbeats and not become candidates. Okay.
So, like with our make function, I'm guessing this is like a race to kick off an election.
Yep.
So when our test starts and there's 3 servers, the first to get instantiated is the first to kick off an election, and that should suppress the other 2 nodes from also kicking off an election simultaneously.
Right.
Others will see new leaders. How to choose election timeout. That's just random. Yeah. At least a few heartbeat intervals in case network drops a heartbeat. So I don't think that was chosen for us in the lab.
Yeah.
So we might create some constants up top, which are like heartbeat interval. Might be like 1 second. Maybe the well, this should probably be set when we instantiate a Raft instance, because
yeah,
the other value we want to set is election timeout interval, and that should be some random number, or however you do that and go. But this should be set per Raft instance. So.
Yep. So it's like between 1 and 5 seconds, I guess, or 5 and 10 seconds, maybe.
Oh yeah, it needs to be some multiple of, well, yeah, like you were saying, at least a few heartbeat intervals. So maybe 3 times rf.heartbeat interval.
Yeah.
Plus some random number of times, like between 0 and 1 times, like you were saying, maybe 5 seconds. So yeah, something like that. Random part long enough to let one candidate succeed before the next starts. Okay, short enough to allow a few retries before a tester gets upset. Why would a tester get upset? Tester requires selection to complete in 5 seconds or less. Okay, so maybe we should set this to 2 seconds.
Oh, so okay, got it. So that's the thing that they have in their tests that we saw earlier.
We can take a look at the tests. This is the first test.
Yeah, some timeout here. Yeah, raft election timeout.
It's I think it's 1 second. 1,000 milliseconds is 1 second. Yeah.
Oh, okay.
The tester generally allows solutions to complete elections in 1 second. Really? That's very short. Interesting.
That is very short. So maybe the paper has a recommendation.
Yeah, it probably has. I mean, it definitely has something to do with internet latency.
Yeah.
Like network latency.
Okay.
Like it's definitely higher if you, depending on your requirements.
Right.
Okay. Okay, this makes starting to make more sense. For sure. Yeah. All right, last paragraph.
What if the old leader isn't aware new leader is elected? Perhaps old leader didn't see election messages. Perhaps old leader is in a minority network partition. New leader means a majority of servers have incremented current term. So old leader with old term can't get majority for append entries, so old leader won't commit or execute any new log entries, thus no split brain. But a minority may accept old servers append entries, so logs may diverge at end of old term. Okay.
Okay. So basically, an old leader should recognize that they're only able to reach a minority.
Yeah.
And they should basically have some way to tell their followers that are now a minority to not not apply to the append entries.
Yeah, but then if the logs diverge, how do they undiverge?
No idea. Maybe there should be some reference tracking of like we master raft instance has these attributes: commit index, last applied index.
Okay.
And also request vote. So
okay.
When a election is kicked off, a new master sends out what its last log index is. I don't know. I don't know how to roll back. Yeah. I don't know how to roll back when the split brain happens.
Okay.
It should tell us. That's fucking sure.
Okay. Well, let's yeah. Okay.
Well, there's a FAQ and question section about the paper. The paper questions is I guess there's lectures paper question, which is definitely not. I didn't know about this. Oh, we're supposed to come up with questions about the paper, like what we find confusing or the paper's context problem. Suppose we have the scenario shown in Raft Papers Figure 7, a cluster of 7 servers with the log contents shown. The first server crashes and cannot be contacted. A leader election ensues for each of the servers marked. Could that server be elected? If yes, which servers would you vote for it? would vote for it? If no, what specific raft mechanisms would prevent it from being elected? So I'm not sure if we're supposed to answer this question. I think we're just supposed to come up with our own question. Straight up. I think that's what they're saying. And
Okay.
that's a homework assignment. Okay, doke.
Okay.
Well, we haven't read the paper, so can't come up with any questions, but I think our question would be exactly what you're just saying, Ben, which is how do you handle a split brain having to roll
Yeah.
back?
Yeah. How do you handle rollback?
I don't know. Maybe I think if we do read the paper, we should read it out of band of the
Yeah.
live stream because that's even just reading these lecture notes is freaking brutal.
Yeah.
So Raft is simpler than the alternatives. Why? What are the trade-offs for making it simpler? I don't know. Is it worth reading this right now?
I don't know.
Wow, this is super long. Let's definitely not read this right now.
Okay.
This is surprisingly long.
Okay.
We can go back to the hints for the part of lab we're on. And where we're leaving off was the election process.
Okay.
So we've kind of implemented their election process. However, we're not keeping track of the state of who's leader, nor are we handling the votes from a given election.
Okay.
So when it comes to handling let's just try and get the votes. Like we're trying to print the vote results for a given election. But yeah, we were looking at the request vote RPC handler, and we definitely haven't finished implementing that. So we're printing that an election is happening, that a given Raft instance is requesting the other Raft instances to vote. And then we're just doing the simple check from the paper, which is vote no to that candidate if their term is behind the
Current term.
the Raft instance's current term. So if they're behind the person they're asking to vote for them, then they should definitely not get a vote.
Yeah.
If voted for is null or candidate ID. So what is voted for again? We're coming back. What was voted for? Oh, so Raft instances keep track of which candidate they had previously voted for.
Okay,
So
got it. Yep.
In a new election, voted for is the candidate they voted for in the last election.
Gotcha.
So first time an election happens, voted for is null.
Yep.
So if voted for is null, and the candidate's log is at least as up to date as the receiver's log, grant vote.
Yep.
So we check both term and log to see whether they're both as up to date as possible or better than the people they're requesting a vote from.
Yep.
So okay, we got started on that. There's this really convoluted Boolean. So that's why I commented out.
Yeah, maybe let's just do ors and ands as ampersands and see if that fixes it.
We can check real quick. And or oh god, not this. Golang cheat sheet, much better. Oh, logical operators. You're right. Double ampersand, double R.
It's too much Python and Ruby.
For show. We are spoiled. Or this language sucks. Just kidding. Cannot convert nil to type int. So Golang check nil if variable is nil. Null detection. Ugh. Ugh. Oh yeah, that's what
Wait,
we're doing.
what line was that? Let's go back to the
Line 157, I think. Yeah. All this is line 157.
cannot convert nil to type int. Okay.
So we're trying to compare an int to a nil, I guess.
Maybe if we just swap the order of the or there. That would be kind of silly, but
I think that it's that the Stack Overflow we were just looking at was if voted for is not is some other type than what this is, which voted for is that int. So so we can, I guess, dereference the get whether, does that make sense?
yeah, maybe.
I don't know if it's asterisk or ampersand in this case.
I don't know about this. Okay, can we go back to the error message again?
Okay.
Cannot convert nil to type int.
So this is because when we call make, we're not setting the voted for value, our new raft struct.
Yeah.
So even though voted for is an int in the struct, so when we're trying to do this heavy duty or this simple comparison,
yeah,
it's failing because this is of type int, or it's expected to be of type int. And so go at compilation time isn't allowing compilation because it's saying you're trying to compare an int to a nil, even though we know this is nil when we first are calling make.
Got it.
So I was Googling about, given that we know, that this key of our struct might be nil because it hasn't been set.
Yeah.
How can we check that or not?
Okay, so on voted for, so we need to do, where do we define voted for in the struct? Up at the top, I think.
Yeah, here.
Yeah, so that should be star int.
Should be a pointer to int?
I think so.
Okay. Okay. Yeah, that eliminated the error message or the compile error. Candidate ID undefined. Oh, that's probably a typo. Yeah, I think it's lowercase d. And then the last, invalid operation. Mismatch types int, star int, and int.
Okay.
Do we need to dereference voted for? Yep. Adding the asterisks here.
Oh, okay.
And then we're trying to do this comparison. I think we want to do length. That's how you get the length of something.
Yep.
But also this log is unassigned, so it's going to say this is nil, I think.
Yep.
Ref.log undefined. Yeah. So in our struct definition of a raft instance, I left this commented out right here. So I guess that fixes it.
Okay.
Although in our make, we're not, with this line still commented out. So it may now fail saying that rf.log is nil. Oh no, it worked. Okay.
We're getting a lot of trues there.
Yeah, but both tests failed. Pretty sure. Yeah. Or test 2A. Did 2A succeed or not? We got a lot of printing going on.
Yeah.
Yeah, the test failed, but it kept printing. Or maybe
Okay.
this was printing even before 2A. No, this is test 2A started.
So
It started doing the election process.
Okay, so now I think we have to keep track of all the votes.
Mhm.
And then if a majority of them come back as true here, then this raft instance is the leader.
Mhm. So we should collect votes somehow.
I think that's my best guess at what the next step is.
If majority of votes are true, the pseudocode. Yep.
Okay.
And then we should probably also emit heartbeat. Right? So that this newly elected leader notifies its peers that it is the new it's the new leader that should be followed.
Yep.
And we can define emit heartbeat as similar to send request vote. We can define an emit heartbeat function that calls append entries with a list of like 0. Does that make sense?
Say that one more time.
So in the election notes, when they're describing what the election process looks like, there's a heartbeat RPC that the leader sends to its followers that it's aware of, or its peers.
Yeah.
All of its peers, whether they're alive or not, or it knows that they're alive or not, which is the append entries RPC. So the append entries RPC here sends an array of entries, which are log entries that the followers should store.
Okay.
And so a heartbeat RPC overloads and uses this append entries RPC, except instead of sending an array of entries, it just sends an empty array.
Okay.
So it can say, I'm not writing any, there's no new events to be written to the log, but I am still the leader.
Yeah. Okay.
So I was just thinking we could make a shorthand function called emit heartbeat. But honestly, we can just say, if we have any append entries RPC anywhere. Yeah, there's no append entries RPC, so I guess they totally expected us to write it. Similar to send request vote. Well, see how request vote is implemented again. So similar to request vote. Wow, we should definitely read the doc string for send request vote. We definitely missed this before. But anyways, what I was going to say is that they are expecting us to write entries.
Yeah.
And we can say it doesn't take any arguments for now, but in reality, it takes all of these arguments. And we probably want to make structs like there are for the request vote RPC.
Okay.
But let's just do that for now. But yeah, it's a method on raft structs. And so all it does is similar to send request vote. Oops. I don't think we need to do this actually at all for this part of the lab. So we can come back to this, but basically similar to send request vote.
Yeah.
We actually might do this because that's how new leaders signal to followers that they are the leader and that the other followers should not try to initiate elections.
Yeah.
Question of whoa, I'm keep up undoing and redoing. So we're going to create an append entries RPC. instead of a request vote args, we'll create an append entries args struct.
Okay.
And an append entries reply. And we can comment this out for now. Just adding a statement here so we can know when it gets invoked. What's it complaining about? Expected statement 202. There we go. So very similarly to how we declared the reply and arg structs here for the request vote RPC.
Yep.
We can create similar for append entries. Okay. So append entries, args and append entries replies are just straight up. We can pull them from the figure in the paper.
Okay.
So term is an int. Their ID is an int. Brief log index. These all need to be capitalized too, so that they can be sent over RPC. Entries. And then the reply just has two items. Term int success equal.
Okay.
So we can add all this as comments in the RPC. In the,
Yeah.
I'll just comment them all out. So I can do that. Okay. So point being is that append entries, this RPC, similar to how we have send request vote when we're kicking off an election, we can create a function like here called Emit Heartbeat.
Yep.
Which very simply, oh man, this looks like it needs a server index. So we might need to, similar to how we loop over all peers to run an election.
Yeah.
We might need to similarly loop over all peers
to send a heartbeat.
Exactly. Yeah. And Emit Heartbeat, unlike send request vote, needs append entries args and append entries implies. Instead of invoking a request vote RPC, we request a append entries RPC. Oof, this is pretty involved.
Yeah, definitely.
Emit Heartbeat might actually.
I think that we could just create our own append entries args in a reply here, but
yeah, because that's a benefit of doing an Emit Heartbeat rather than a send append entries wrapper to the RPC. Although we could do it either way.
Yeah.
We can call this send heartbeat. Args equals reply equal. Okay.
All right.
This is all being done in commented code, which isn't very helpful. But
yeah.
All right. So we were going to handle the election results.
Yeah.
We're not doing currently. So how the hell do we collect these votes? We have reply objects, reply variables for each
Yeah.
each peer we've sent a request vote for.
Yep.
And as we saw in our test output, we're largely getting back these votes of true. So the value is being set.
Yeah. So maybe we should create an array of like votes or something.
Okay.
Yeah.
Okay, make a slice of bools. Is that right?
Yep. And then here, when we get a reply, we should first check that the term is the same term that we sent, maybe.
Was that something that I missed in the lecture notes?
No, but I'm guessing that would be why it's asking for the term to be returned.
The request vote RPC has this vote or current term for candidate to update itself. So if an election is being kicked off, like this block of code we're looking at is running.
Yeah.
And then RF is the current Raft instance that is the candidate who's kicked off the vote. And so, like you said, we need to set current term equal to if reply dot term greater than the current term. Is that right?
Yeah.
Then we overwrite
something.
Our candidate's term.
Yeah. We have to use term, otherwise it wouldn't be necessary. It wouldn't be part of the results.
Mm-hmm. Yeah. So we're bringing our candidate's term up to date with the peers that we're asking to vote for us.
Okay.
So when does the term get incremented? Shouldn't the candidate be the one to increment the term? Like, since I'm a candidate, since I'm a Raft instance, a member of our cluster, and I don't have a leader yet, and I want to kick off an election, shouldn't I be the one that increments my current term and then notifies my peers that there's a new term? Does that make sense?
Yeah. Yeah.
Oh, in fact, yeah, that is what we are doing on line 305. We're telling our peers, hey, I want to start a new term.
Right. But it doesn't get incremented.
Yeah. And the arg to the request vote RPC is provided by the candidate. Okay. Maybe we should send current term +1 and then do what we were doing before, which was this resetting the candidate's term based on what the voter picks back.
Yep.
Although this receiver implementation section of the paper doesn't say anything about what the result term should be.
Can we look at what we have? The vote.
I think we just telephone back the same thing that we were handed.
Same term, yeah.
That would be in request vote, right?
Yeah. So maybe here we return not arg's term, but our term. rf.current term.
Should probably do that up here. It's the same whether, regardless of which if clause gets evaluated.
Yeah. I mean, it's gotta return our current term because the candidate already knows the term that it wants.
The thing is, if the term that's being initiated a vote for is greater than our current term, maybe we should be updating our current term, right?
Yeah, but it doesn't say anything about updating current term in the request vote RPC.
Yeah, that's true.
I just think the reply should be the current term. I think that makes sense.
Okay.
Let's try that.
Should probably also log our accept term. So we can see, okay, raft instance 1 is requesting a vote of 2 for term 0, or for term 1, for the first term.
On conversion to candidate, start election, increment current term.
Were you reading that?
Rules for server.
Shit. Yeah, we've. I was like, ding. There's a little section and I forgot we hadn't read it yet. I'll make the text bigger. Okay, all servers. If commit index greater than last applied, increment last applied. Apply log last applied to statement. This is referring to the append entries RPC, I think.
Okay.
If RPC request or response contains term T greater than current term, set current term equal to T, convert to follower.
Okay, so yeah, maybe you're right. So all server, if RPC request or response contains any term that's greater than the current term, always set the current term to, yeah.
And we gotta say is leader equals false.
Yeah.
That seems aggressive though, right? Like, let's say a raft instance is like, I don't know who the leader is. I want to become a leader. Let me hold an election. And increments the current term.
And then that invalidates every other
leader.
Yeah.
I guess, yeah. Well, that should get caught by one of the labs tests.
Well, maybe that scenario just shouldn't ever happen. Really, like no node should just be randomly like, I want to be leader. Although I guess we have to assume that that's going to happen at some point. I don't know. Okay.
Well, let's keep reading the paper.
There's a lot of layers to peel back here.
Let's keep that commented out for now, because I agree with you. This is a little weird, right? So what I was just seeing here is candidates on conversion to candidate start an election. Okay. Increment current term. We now do that in the make in our kicking off an election. We don't. We should do they have the syntax in Go? So yeah, let's increment the current term because we're kicking off an election and we are a candidate.
Okay.
Vote for self. Okay. That's important to remember since we don't have it. And reset the election timer, which we don't have yet. Send request vote RPCs to all other servers. That we are doing that. If votes received from a majority of servers, become leader. Okay, let's just do that for now. If append entries RPC or C from new leader, convert to follower. Okay, that's something we can do in the append entries RPC, which we've barely started.
Okay.
If election timeout elapses, start new election. So something we should definitely not do when we do our sending of heartbeat is that we should say if I equals rf.me, we should not send ourselves a heartbeat. Because
Okay.
that'll take us out of being a leader or being the leader.
Right. Okay.
So I don't know if Go has the continue syntax. Do you know if it does?
I do not. It's got to have some kind of continue or next.
If break, they do have continue. They do.
Okay.
So basically, what this does is it says if the index of our peer is ourselves, so don't skip ourselves in this for loop so that we don't send ourselves a heartbeat.
Right.
And which would, since it's an append entries RPC, like the paper says, we should not set ourselves a leader as a follower every time we send a heartbeat.
Okay.
Okay, I think this is a good time to take it off, take a break, come back another time.
Yeah, let's take a break. Maybe let's read up more on Raft. There's this the notes point to a like a tutorial, an illustrated guide.
Mm-hmm.
Maybe that would be useful to do in our time.
Okay. Yeah. Let's play it by ear about when we do this next. And sync up about how much reading we're willing to do outside of band of the lab.
Cool.
Okay, dude. This has been awesome.
Cool. Yeah, this was awesome.
I don't think we got any chats, which sucks. So if you're watching this, come to our next live stream, hang out in the chat, ping us if you've got questions. Subscribe to the YouTube channel so you get notified of new events we're doing live stream wise, or posting new video wise. Ben, do you want to shout out to anybody?
Shout out to all of our viewers, all 5 of you or 6 of you.
Oh, rad.
Yeah, I think so. Like, I like this because it's material that I've not done before, like Raft. I've not implemented Raft before, but maybe we could do like some smaller ones that just focus on like Go syntax, like more like we're trying to understand Go and we're trying to understand Raft here. Maybe it'd be easier to first try to understand Go more, like do like a channels exercise or a RPC exercise. I don't know.
Honestly, I agree with you about the best way of learning a language is jumping in the deep end.
Yeah.
And honestly, like you just said, I feel like I know Go better than I know Raft at this point, which isn't saying much.
Totally. But so I understood MapReduce. So jumping into a MapReduce Go thing, it was like, oh, okay, I'm learning Go on the way, but I don't understand Raft. So jumping into Raft and Go, it's like, okay, what's going on? You're kind of learning 2 concepts at the same time. Does that make sense? Like, why? Like, I don't know.
I think if we go back and we rewatch this live stream, you and I, that we will. I think a minority of the time we spend on the live stream is figuring out Go.
Yeah.
And I think it's because we really are dealing with the coursework versus learning the programming language.
Yeah.
Which is totally what I think a lot more people are interested in the course content than
the Go
honestly,
content.
than the Go content. So I think we're doing right by our audience, but our audience should feel free to correct me here. drop a comment. Right. Tell us we suck. Tell us what you'd like to see more of rather than telling us we suck.
Yeah.
Um, but
Yeah,
it,
I
no,
mean,
we
there's
yeah,
the fun algorithm, I guess. I'm learning a lot about consensus and Raft.
yeah. I think what would be super awesome outside of doing these problem sets is that there are some very, very real world applications of the concepts that we're doing or
Yeah,
learning in this course, uh, particularly when it comes to highly available
yeah,
services, which is an extremely interesting topic for a lot of different areas of software,
totally.
uh, banking, finance, cryptocurrencies, something that I don't know if
Yeah,
either me or Ben know a great deal about.
I do know it's
Uh,
distributed.
it's distributed. There's a blockchain, aka a log,
Right.
a distributed log, which sounds familiar.
Yeah.
Although I don't think they use Raft.
Yeah.
uh, who knows? I think what will happen is we'll get through more of these labs, and when we finish the course, and if people follow us all the way through, we'll be really well equipped if we want to um, do a different course or look at
Yeah.
some existing in the wild open source projects that are distributed systems
Yeah.
like the Kafka code base. Although I think the Kafka code base is Java,
Yeah.
not positive about that. Or it might be C++, not positive about that. But
I'm
I've
sure there are a
seen,
ton of other code bases in Go that are doing this exact or similar thing, I'm sure. Just
yeah,
fault
yeah.
tolerant.
I came across a Go GitHub repo called Jocko, Jocko, that is a reimplementation of Kafka in Go.
Mm.
And Kafka, if any of you guys in the audience or Ben, you're familiar, if you actually try to run it, for example, on your laptop or in the cloud, it's actually not just a single executable process. You don't
Right.
just run Kafka and it
Yeah.
runs the server. You actually need a second process called Zookeeper,
Yeah.
which
Which I think is
yeah,
just the consensus piece. Like it's Zookeeper
totally.
purely holding the state of the consensus, and then Kafka is built on top of that,
Mhm.
which is similar to what we're doing here. We're building Raft, which is our consensus, and the next lab we're going to build a key value store on top of that consensus, right?
Yeah. So Jocko is a Golang implementation of Zookeeper plus Kafka. So in some ways, it's simpler to administrate than if you go and try to use Kafka on your laptop for
Right.
development work.
Right.
Um, and I think it's a pretty young open source project. It's definitely not used in production, I don't think, by anybody. But as far as for our audience goes and for ourselves, what might be cool in the future after the course is to go and look at code bases like that, potentially contribute to them, potentially look at what they're doing. Something I'm pretty interested with Go is while it's type safe, and we're working with tests written by the professor of this course. It would be cool to create some patches for something like Jocko.
Oh, right. Yeah.
Um, there's a ton of distributed systems projects we can look at, but
Yeah.
we can do that out of hand.
Cool.
But yeah, I'm glad we had this conversation live so that our audience can kind of get a sense of what it is we're going for, and
Right.
they can give us feedback about why they find what we're doing over the course of 3 hours interesting.
Right. Yeah.
Uh,
Well, as long as it's interesting to us, that's all that really matters.
yeah, for sure, for sure.
Cool.
But yeah, otherwise, let's say peace to our fans. I want to
All
say
right.
thanks to the fans. Hi, mom. All right.
Hi, Mom.
See you guys next week.
All right. See you.